So according to Huygens principle, all points of a wavefront of light in vacuum or in transparent medium may be regarded as the new source of secondary wavelets, which gives rise to spherical wavelets, which propagate with the same velocity as the original wavefront, and the wavefront at any later instant may be regarded as the envelope of these secondary wavelets. Right? So if you disturb a particular wavefront, then it will produce spherical wavelets, secondary wavelets. These wavelets will give the wavefront at any later instant. Right? So this was the this is the Huygens principle. Now after that, Fresnel added something with this Huygens principle, and he has named it Huygens-Fresnel principle. Right? So this principle we have written all full portion, that is all points of the wavefront of light, then this portion dash dash as the envelope of these wavelets, as the envelope of these wavelets. Then he add only one sentence. The sentence is, these secondary wavelets mutually interfere. These secondary wavelets mutually interfere. Fresnel only add this sentence, and he gives the name of this principle is Huygens-Fresnel principle. So the importance of this Fresnel addition is an or we can say it is a very much importance. Otherwise, we cannot explain the phenomena of interference diffraction. If it will produce only secondary wavelets and it will gives the wavefront, then if it is not interfere, then we cannot explain. But interference diffraction, that is the phenomena of interference, that is interfere these secondary wavelets. But Huygens will not say that this secondary wavelet interfere. He has not said this thing. But Fresnel says that these secondary wavelets mutually interfere. Right? So without interfere of these secondary wavelets, we cannot explain the interference, the phenomena of interference. So the point that secondary wavelet mutually interfere is an important conclusion, right? By considering the experimental observation, right? So to explain that interference experiment, we need this statement, that is, the secondary wavelets must interfere, mutually interfere, right? So this is the Huygens-Fresnel principle. Now, Huygens says the amplitude of the forward wave is maximum and backward wave is minimum, 0, right? And practically, backward wave does not exist, right? If you disturb a wavefront, suppose for these 3 points, then it will gives you the spherical wavelets, secondary wavelets, and any later instant you can consider the wavefront that will be regarded by this secondary wavelet. So in the backward direction, this is the wavefront. In the forward direction, this is the wavefront, right? So now you consider, that means since it will produce a spherical wavelet, so it can have the both in the forward direction and also in the backward direction. But in practice, we can observe the existence of this secondary wavelets in the forward direction. There is no existence of the backward direction, right? So these things only he gives the statement that amplitude of the forward wave is maximum and backward wave is minimum and 0. And physically backward wave does not exist. Now later on, to explain, if you consider the intensity distribution in interference or in diffraction pattern, then that intensity is proportional to this term, 1 plus cos theta. Intensity is proportional to cos theta. What is theta? Theta is the angle between the direction of propagation and the direction under consideration, right? Theta is the angle between direction of propagation and direction under consideration. Now, suppose if we consider this particular direction of consideration, and direction of propagation is like this direction. So here theta is equal to 0. So that will gives you the intensity is proportional to 2. That is the maximum. Now if we consider the direction of propagation, this direction, and direction of consideration is opposite. Suppose this backward direction, then cos theta equal to 180. So that 180 will gives you the 0, intensity is 0. So that can be explained with the intensity distribution in interference pattern, right? So we will observe this type of term is present in the intensity expression, right? So that indicates the existence of forward wave, but there is no existence of backward wave, right? Now we come to the interference of light. What is interference? The phenomena of redistribution of light energy due to superposition of light waves from two or more number of coherent sources is called interference of light, right? So if we consider the superposition of two or more number of light waves from two or more number of coherent sources, right? Then we will get redistribution of light energy on the screen, and that pattern is the interference pattern, and phenomena is known as interference of light, right? The phenomena of redistribution of light energy due to superposition of light waves from two or more number of coherent sources is known as interference. So now you consider this is the light source. So it will gives you wavelets. Then it is disturbed by these two pinhole. And then from these two pinhole, we will get secondary wavelets. And these secondary wavelets will mutually interfere. And where it will mutually interfere in this region, you see, this is the maximum intensity that indicates the bright fringe. And in this region, you see they interfere, but in opposite phase, right? Their phase is different. So in opposite phase, they will interfere in this region. So that will produce the dark region. And again, here it will produce the interference in the in phase condition. So that will again bright. So in the screen, we will get a bright dark, this type of intensity distribution. So this is basically is known as the redistribution of light energy, as if light energy is drawn from this region and it is gathered in this region at the position of bright fringe. Point is clear? It is mentioned here also. In the constructive interference, the amplitude of the resultant wave is greater than that of the either individual wave. In case of constructive, because this bright position, this is the position of constructive interference, this intensity is greater than the individual intensity of the wave. If one slit is closed, then from due to one slit, what is the intensity distribution? But when both are open, then this intensity at the position of bright fringe is not equal to the sum of these two intensity, but it is more than that, right? So this is the redistribution. In destructive interference, the amplitude of the resultant wave is less than that of the individual wave. In case of this dark position, the resultant intensity is less than the individual intensity, right? So this is light energy is drawn from this region to this region. Now we consider the theory of interference. Now let us consider two sources. It is mentioned schematically. This is your source, original source, and then light will fall on these two sources, S1 and S2. These two are pinhole, S1 and S2. Their separation is D, and they will produce the interference pattern on the screen. We consider any point P on the screen, and we want to determine the intensity at this point, right? Now, at central position, this is your central position, right? If we consider from these two sources at central position, then it will also produce some interference pattern. So within the screen, P can have any point, and then if we calculate the intensity at point P, then we can find it out the intensity for any particular value from this central position or even at central position, right? Now we consider the path from S1 to P is R1 and S2 to P is R2. Now these 2 points, that is the pinhole S1 and S2, is equidistant from S, right? Is equidistant. That means the length of this path and this path is equal, right? Length of S1 and S2 are equal, and only the path introduced at point P, path difference introduced at point P due to from these two sources S1 and S2 or pinhole, we can say, right? So S1P and S2P are not equal. It will be equal when it will be in the mean position, that is at the central position, right? Otherwise there must be different path. Now the path difference that we can calculate if you draw one normal from this SP to this S2P, right? So this is the normal, this angle is 90 degree. So from this point to P and from this point to P is the same path. So path difference is this portion. That is, I have mentioned here PD. That is the path difference. So what is this path difference? That we need to calculate. And another thing, you can see here that from the central position or in the mean position of this, the source S1 and S2 are located at a distance of d by 2, because the separation between these two sources is d. So this portion is d by 2 and this portion is d by 2, right? Now we see. Let us consider S1 and S2 are two closely spaced narrow slits and equidistant from S as shown in figure below. Further, we consider that the fields at point P on the screen due to S1 and S2 are Y1 and Y, right? We consider the field at point P due to S1 and S2 are Y1 and Y2, where Y1 is A1 sin omega t. Y1 is A1 sin omega t and Y2, that is equal to A2 sin omega t plus delta. Y2 equal to A2 sin omega t plus delta, where A1, A2 are the amplitude of the field at point P. A1 and A2 are the amplitude of the light field at point P, right? Okay, now we consider here this delta, that is Y2 equal to A2 sin omega t plus delta. Here delta is the phase difference due to path difference, because these two rays, that is S1P and S2P, are not equal path, right? So there is some path difference is there, and this path difference will gives you a phase difference, right? The equivalent phase difference is delta. We consider here. Here delta is the phase difference due to path difference between S1P and S2P. According to the principle of superposition, you can write the resultant field at point P. The resultant field at point P due to superposition, we will get Y equal to Y1 plus Y2. That is A1 sin omega t plus A2 sin omega t plus delta. Now, if we expand this, that is sin omega t plus delta, that is sin A cos B cos A sin B, like that, right? So A2 sin omega t cos delta plus A2 cos omega t sin delta. Now, from this, if we take sin omega t is common from these two terms, that is A1 plus A2 cos delta sin omega t. And here you consider A2 sin delta cos omega t. Now, this quantity is equal to A cos phi, and this quantity is equal to A sin phi. We take, that is A1 plus A2 cos delta, that is A cos phi, and A2 sin delta, that is equal to A sin. Right? So under this consideration, you can write A sine omega t plus phi, right? So y equal to A sine omega t plus phi, where A can be determined from this, right? So if you take square and add this, if you take square and add this, then a square equal to a1 plus a2 cos delta square plus a2 sin delta square, right? So that's mean a square equal to a1 square, a2 square twice a1, a2 cos delta. And phi, that is equal to sine. If you divide this equation by this, that is tan phi, that is a2 sin delta divided by a1 plus a2 cos delta. Now, this square will gives you the intensity, because this is the resultant amplitude. This is the resultant field amplitude at point P. Capital A indicates the resultant field amplitude at point P, and a square equal to this. Now you know that is I is proportional to a square. That is intensity. Intensity at a particular point is proportional to the square of the amplitude, right? So I is proportional to a square. Therefore, you can write I, this quantity is I, then this A1 square, that is equal to I1, A2 square, that is equal to I2, and then twice A1, A2, that is root of I1, root of I2, and cos delta. So from this expression, if you consider that is I1 equal to I2 equal to I naught, then this is twice I naught, and this is also twice I naught. So we take common twice I naught, 1 plus cos delta, right? Previously, to discuss that Huygens principle, we have mentioned that intensity is proportional to 1 plus cos theta. 1 plus cos theta. So you can see according to interference, we will get I equal to twice I naught, 1 plus cos delta. Point is clear? So this is the resultant intensity at any point P on the screen. So resultant intensity is I equal to twice I naught, 1 plus cos delta. Is it okay?
Yes, sir.
Now we consider the constructive interference. In case of constructive interference, you know the intensity is maximum. It happens when cos delta equal to 1, because here 1 plus cos delta. So when cos delta equal to 1, then you see 1 plus 1, 2, 2 multiplied 2, that is 4 I naught. The intensity is maximum, right? This quantity will be maximum when this cos delta will be plus 1, and intensity will be minimum when this cos delta equal to minus 1, because these are the constant quantity, only this is a variable, right? So cos delta maximum value is plus 1 and minimum value is minus 1. So intensity will be minimum when cos delta equal to minus 1, and that intensity is 0, and maximum intensity is 4 I naught. So it happens when cos delta equal to plus 1, that means delta equal to twice n pi. When cos delta equal to 1, that means delta equal to twice n pi, where n equal to 0, 1, 2, 3 natural number, right? 0 including 0, or plus minus 1, plus minus 2, this. Thus corresponding path difference. Here the phase difference is twice n pi. Then what will be the path difference? The relationship between path difference and phase difference is this. This is the path difference, that is lambda divided by twice pi into delta. So delta is twice n pi. So twice pi will be cancelled out. So that means n lambda. That is equal to twice n lambda by 2. We can write twice n lambda by 2. This is the intensity maximum. So the path difference is equal to n lambda, that will gives you the maximum intensity. When path difference between these two interfering beam is n lambda, then we will get the maximum intensity. Now, in case of destructive interference, intensity is minimum. So when it will happen, that is cos delta equal to minus 1, or delta equal to twice n plus 1 into pi. In that situation, delta equal to twice n plus 1 into pi. Thus, corresponding path difference. Under this situation, what will be the path difference? Path difference will be lambda divided by twice pi into delta, that is twice n plus 1 lambda by 2. Because twice pi will be cancel. Pi will be cancelled out. Right? So twice n plus 1 lambda by 2. Intensity is minimum when the path difference is odd multiple of half wavelength. Intensity will be minimum when path difference is odd multiple of half wavelength. And intensity is maximum when path difference is even multiple of half wavelength. Point is clear? Now, this is the intensity distribution. At 0, twice pi, 4 pi, here also twice pi, 4 pi. You see, this is the maximum intensity. At that maximum intensity is 4 I naught. At the value of minus pi, plus pi, thrice pi, minus thrice pi, you see the intensity is 0. Right? And in between, the intensity is within the limit 0 to 4 I naught. Right? So intensity will oscillate like this. If you consider within the screen, then we will get this is the maximum intensity bright spot, then 0 bright spot, like this way. This intensity pattern shows that redistribution of light energy, but the average intensity over a period, if you consider the average intensity over a period, that is 0 to twice pi, if you calculate, then that will be the sum of the individual intensity. That is I average, that is 1 by twice pi, 0 to twice pi, I d delta. First semester. 1 by twice pi, 0 to twice pi, I d delta. So if you integrate it, then we will get the intensity expression, that is twice I naught, 1 plus cos delta d delta. Right? So if you integrate, then contribution from this term over a period, that will gives you twice pi. So twice pi will be cancelled out and we will get twice I naught. This contribution will be 0 over a period twice pi, right? Which indicates conservation of light energy. This indicates the conservation of light energy, because if a single source or single slit is open, then intensity is I naught. When both will be open, then we will get the redistribution of light energy. But the average intensity on the screen, that is equal to twice I naught, right? So it indicates the conservation of light energy. Now, if you look this picture, and if we consider that this is your central position, and at this central point, your path difference is 0, because this path, that is S1P, O, so S1O and S2O, this will be same, that is equidistance. But for all other points, the path is different. So what will be the path difference in terms of this y, small d and capital D? Capital D is the separation between source and the screen. D is the separation between two sources, and y is the position of a particular fringe position, right? A particular fringe position, that is at point y, the separation from your central position is y. So what is the path difference? This path difference in terms of d, small d, capital D and y. Now from this figure, the path difference PD, that is R2 minus R1. But from diagram we can write R2 square. What is R2 square? R2 square, that is equal to, this is a right angle triangle. This. So this R2 square, that is equal to D square plus Y plus D by 2 whole square. D square plus Y plus D by 2 whole square. And R1, that is equal to D square plus Y minus D by 2 whole square. Y minus D by 2 whole square. Then R2 square minus R1 square. So this D will be cancel out, and Y plus D by 2 whole square minus Y minus D by 2 whole square. So that will gives you twice Y into D. So after simple mathematical steps, you will get twice Y into D. Now this R2 square minus R1 square, that you can write R2 plus R1, R2 minus R1. Now R2 plus R1, this quantity is nearly equal to twice D. This quantity is nearly equal to twice D, right? Since capital D is very large compared to your small d, then R2 and R1 are both nearly equal to D. So we can write R2 plus R1 nearly equal to twice D. So R2 minus R1, that you divide it by twice D, twice YD divided by capital D. So the path difference, that is R2 minus R1, that is YD by D, right? This is the optical path difference between two interfering waves at point P. At point P, the path difference is YD divided by capital D, where Y is the separation at that point P with respect to its central position. This point is clear?
Yes, sir.
Yes, sir.
Now we consider the fringe width. Fringe width, if we consider for constructive interference, then R2 minus R1 is even multiple of lambda by 2. For constructive interference, R2 minus R1 is even multiple of lambda by 2. So in that situation, path difference, that is R2 minus R1, that is equal to twice n lambda by 2, where n equal to 0, 1, 2, and this number, right? Now, according to this path difference, R2 minus R1, that is Y D by capital D. Now, if we consider that Y is the position of nth order principal maximum, if Y is the position of nth order bright fringe, right? Y is the position of nth order bright fringe, right? If it is nth order bright fringe, then we can write Y equal to Yn. That is, nth order bright fringe is located at a distance Yn from your central position. Then R2 minus R1, that is Yn D divided by capital D. That is equal to twice n lambda by 2, right? So that means Yn equal to lambda n lambda D divided by small d, right? Yn equal to n lambda D divided by small d. Now, if we consider the next bright fringe, the next bright fringe is located at position n plus 1th position. That is Yn plus 1. The position of the n plus 1th order bright fringe is Yn plus 1. So in that situation, Yn plus 1 will be n plus 1 lambda d by d. N plus 1 lambda d by d. So the separation between this nth and n plus 1th order bright fringe, the separation between nth and n plus 1th order bright fringe, that is lambda d divided by lambda capital D divided by small d. So this is the fringe width. Fringe width is lambda d divided by small d. And similar way, if we perform this treatment, that if the width position of nth order dark fringe, then yn d divided by d, that is equal to twice n plus 1 lambda by 2, and then yn, that is twice n plus 1 lambda d divided by twice. And if we consider again n plus 1th order dark fringe, which is also located at position, that is n replaced by n plus 1, that is 2 into n plus 1 lambda d divided by twice d, that is equal to twice n plus 3 lambda d divided by twice d. And if you take this difference, that is beta equal to fringe width beta equal to yn plus 1 minus yn, then again you will get lambda d divided by d, right? Again you will get lambda d divided by small d, right? So therefore we can conclude the spacing between any two consecutive dark or consecutive bright fringe is same, and its value is lambda d divided by d, which is known as the beta, that is the fringe width of two consecutive bright fringe, right? The separation, not we say width, the separation between two consecutive bright fringe, or we can say the separation between two consecutive dark fringe, or the total width of a bright fringe and a dark fringe, right? That is the fringe width. Fringe width is total width of one bright fringe and one dark fringe, or we can say the separation between two consecutive bright fringe or two consecutive dark fringe, right? That is the fringe width. Now another thing, angular fringe width. Angular fringe width. The angular fringe width is defined as the angular separation between two consecutive bright or dark fringe. This is the linear separation, that is lambda d divided by d. That is the fringe width, linear separation. Now angular separation. The angular fringe width is defined as the angular separation between consecutive bright or dark fringe, and it is denoted by omega, that is theta n plus 1 minus theta n, where theta n is the position of n plus 1th order fringe, either bright or dark, but we have to consider consecutive, either two consecutive bright or two consecutive dark. So theta n plus 1 is the position of n plus 1th order fringe, and theta n is the position of nth order fringe. Then angular separation between these two fringe, that is omega equal to theta n plus 1 minus theta n, that is equal to yn plus 1 divided by d minus yn divided by d, right? Theta n, that is yn plus 1 divided by d minus yn by d. So that is equal to lambda divided by d. Lambda divided by d. So that is angular fringe width. If you divide it by d, capital D, then we will get the angular fringe width, that is equal to lambda divided by d, right? So this is the linear fringe width, lambda d divided by d, and angular fringe width, that is lambda divided by small d. Point is clear? Now we consider the condition of interference. Condition of sustained interference. In sustained interference of light, the interference pattern should be stable and observable, right? In these situations, for self-sustained interference, that is, interference pattern should be stable and observable. The condition of sustained interference, first condition, that is the interfering wave must be coherent. The interfering waves must be coherent. That interference will produce by two or more number of coherent light waves that we have mentioned in the definition. So the interfering wave must be coherent. Two sources of light are said to be coherent if they have a constant phase relationship between them. They must have the constant phase relationship. That means their phase difference will be remain unaltered. It will be same. The phase difference will be remain same, right? It may have some constant value or it may be, right? The interfering wave must propagate in the same direction. Interfering wave must propagate in the same direction. The interfering wave must have same amplitude to get maximum visibility. To get the maximum visibility, the interfering wave must propagate. Amplitude of the interfering wave will be equal, same amplitude, right? The interfering wave must be monochromatic and same frequency. The interfering wave must be of same frequency, that monochromatic. The interfering wave must have same state of polarization. The interfering wave must have same state of polarization. What is polarization? That we will discuss later on. It is a separate chapter we will discuss later on. But they must have same state of polarization. The coherent sources must be narrow and separation between them must be small. The coherent sources must be narrow source and they have small separation, right? Their separation will be small. If its separation is not small, if small d is large, then what will happen? Fringe width will be very narrow. Fringe width will be very narrow because fringe width is lambda capital D divided by small d. So separation between two sources is small d. If it is large, then fringe width will be very small, right? Then we cannot detect properly the maxima and minima. So that's D, the separation between two source will be small, right? So these are the condition of self-sustained interference pattern to observe the interference pattern. Okay. This point is
sir.
clear?
Yes, sir.
Okay. So I will stop it here today. Next week we will continue. And perhaps next class, Dr. Sahu will take the next class, right? Friday you have class at 9. So Dr. Sahu will schedule and he will take this class. Okay,
Sir,
thank you all.
what another topic?
Other topic, obviously.
Thank you, sir.
Okay, thank you all.